Look up at the night sky, really look at it. Those shimmering dots aren't just stars, they're unanswered questions, mysteries waiting to be unraveled. Now picture this, the swirling colors of the pillars of creation, a cosmic nursery where stars are born, or the haunting glow of a distant nebula, its secrets locked in light that traveled millions of years to reach us. These aren't just beautiful images, they're puzzles, and for centuries, humanity has tried to solve them with two powerful tools, science and imagination. What if the greatest discoveries in the universe didn't come from equations alone, but from the dreams of those daring enough to ask, what if? Think about it. Black holes were once just a wild idea in the mind of a physicist named Carl Schwarzschild, a mathematical curiosity that seemed too strange to be real. Fast forward a century, and we've not only proven they exist, we've photographed one, a dark monster bending space itself. Exoplanets, worlds beyond our solar system, were the stuff of science fiction until astronomers turned speculation into fact, finding thousands of them in the cosmic deep. These breakthroughs didn't happen because someone stuck strictly to the data. They happened because someone dared to imagine the impossible, then used science to chase it down. That's the journey we're about to take, a voyage where the line between fact and fiction blurs, where the universe's biggest secrets are uncovered by the marriage of logic and wonder. We'll explore how visionaries from Galileo to Carl Sagan didn't just study the cosmos, they conversed with it, asking bold questions and letting their imaginations guide the way. From the birth of stars to the edge of reality itself, this is the story of how human curiosity, fueled by both equations and dreams, cracks open the universe's greatest mysteries. So buckle up, by the end you might just see the night sky and our place in it a little differently. Long before telescopes or satellites, humans looked up and saw more than just stars, they saw stories. The night sky was humanity's first canvas, where ancient civilizations painted their myths, fears, and dreams. In Mesopotamia, they traced the wanderings of planets and named them after gods, believing celestial movements held divine messages. The Greeks spun tales of Orion the hunter, forever chasing the Pleiades across the heavens, while indigenous cultures saw the Milky Way as a river of spirits or a pathway to the ancestors. These weren't just fantasies, they were the first attempts to explain the unexplainable, to bring order to the chaos above. But then came the thinkers who dared to ask, what if there's more? Around 2,600 years ago, a Greek philosopher named Thales dropped a bombshell. He suggested that natural laws, not capricious gods, governed the cosmos. It was a quiet revolution. Centuries later, Galileo pointed his crude telescope at Jupiter and saw moons orbiting it, shattering the old belief that everything revolved around Earth. Suddenly, the universe wasn't a stage for myths. It was a machine with gears we could understand. Yet here's the fascinating twist. Even as science stripped away the old stories, it replaced them with something just as wondrous. That's the magic of cosmic curiosity. It doesn't discard imagination, it refines it. The Greeks imagined Apollo's chariot pulling the sun because they had no concept of a nuclear furnace floating in space. But when science revealed the truth, the wonder didn't fade, it deepened. Think about it, the same human mind that once dreamed of celestial chariots now calculates black holes and builds probes to touch the sun. The tools changed, but the hunger to know, to connect remains. Whether it's an ancient astronomer charting the stars on a clay tablet or a modern scientist decoding the afterglow of the Big Bang, the drive is the same. We look up, and in that act, we find both answers and new questions, each discovery a stepping stone to the next great mystery. Johannes Kepler once listened for music in the motion of planets. At a time when telescopes were still new and crude, this mathematician became obsessed with an idea straight out of Greek mythology, that celestial bodies moved in perfect harmonies, singing a cosmic song only mathematics could decode. He scribbled notes comparing planetary orbits to musical intervals, convinced the universe followed hidden rhythms. What sounds like poetic fantasy today was revolutionary science then. Those wild imaginings led Kepler to his 3 laws of planetary motion, the foundation of modern astronomy. The same man who dreamed of celestial melodies gave us the tools to calculate orbits with precision. Then there's Isaac Newton and his famous apple, a story so enduring it skirts the line between fact and folklore. Whether the fruit actually bonked him on the head matters less than what it represents, a moment of playful curiosity colliding with rigorous thought. Newton didn't just see an apple fall, he wondered if the same force tugging it earthward might also hold the moon in orbit. That leap, from everyday observation to universal law, captures the essence of scientific discovery. Gravity wasn't uncovered through dry calculation alone. It took a mind willing to ask whimsical questions and chase them to their logical extreme. Carl Sagan put it best when he said, "Imagination will often carry us to worlds that never were, but without it, we go nowhere." Look at modern astrophysics, where some of our boldest ideas still outpace proof. Take dark matter, an invisible substance making up most of the universe's mass. We've never directly seen it, yet its gravitational fingerprints are everywhere. Or consider wormholes, those hypothetical cosmic shortcuts born from Einstein's equations. Scientists treat them seriously not because we've found one, but because the math allows it and imagination dares us to look. This dance between speculation and evidence never stops. When Einstein envisioned riding a beam of light, he wasn't running experiments. He was conducting thought experiments, letting his mind wander where instruments couldn't yet follow. Today's researchers do the same, simulating black hole collisions on supercomputers or theorizing multiverses. The process hasn't changed since Kepler's day. First we dream, then we calculate, then we build tools to close the gap. Every paradigm shift begins not with a eureka in a lab, but with someone staring at the stars and whispering, "What if black holes were once the stuff of pure fantasy, lurking in the edges of human imagination long before telescopes could prove their existence?" Back in the 1700s, an English clergyman named John Michell proposed something radical. What if there were stars so massive, so dense, that not even light could escape them? He called them dark stars, a poetic term that captured the eerie essence of these cosmic traps. At the time, the idea seemed more like philosophical musing than physics, a curious footnote in history rather than a serious scientific pursuit. But Mitchell's intuition was uncanny. He'd unknowingly sketched the first rough draft of a black hole. Fast forward to the early 20th century, when Einstein's theory of general relativity rewrote our understanding of gravity. His equations predicted the existence of objects so dense they'd warp space-time into a one-way street, yet even Einstein hesitated to accept their reality. It took Karl Schwarzschild, a physicist working on the front lines of World War I, to solve Einstein's equations in a way that revealed the mathematical inevitability of black holes. Even then, many scientists dismissed them as theoretical oddities, too strange, too violent to exist in our universe. But while academia debated, science fiction ran wild with the idea. H.G. Wells' The Time Machine hinted at the crushing grip of gravity, and later authors like Arthur C. Clarke painted vivid portraits of these cosmic monsters. Black holes became a staple of space opera, gateways to other dimensions or time-bending traps. For decades, they lived in this limbo, half myth, half math, until observations caught up with imagination. The discovery of Cygnus X1 in the 1970s changed everything. Here was a real black hole, its gravitational pull stealing matter from a companion star, proving Mitchell's dark stars were more than just a dream. Then came the ultimate collision of science and pop culture, Kip Thorne's work on Interstellar. The film's depiction of Gargantua, a spinning black hole with its luminous accretion disk, wasn't just artistic license. Thorne and a team of physicists ran equations for months to render it accurately, leading to a startling discovery. Their visualizations showed light bending in ways that revealed new details about gravitational lensing. Hollywood's fiction had looped back to fuel real science, proving that sometimes the boldest cosmic truths emerge when we let imagination and calculation dance together. Today, as telescopes like the Event Horizon capture actual images of black holes' shadowy silhouettes, we're witnessing a new chapter, one where the wildest ideas of the past become the data points of tomorrow. Enrico Fermi sat down to lunch with his colleagues one ordinary day in 1950, and between bites, he asked a question that would echo through the decades. Where is everybody? It seemed simple enough. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars. Statistically, life should have emerged elsewhere, maybe even civilizations far older and more advanced than ours. So why, in all our searching, have we found nothing but silence? That's the Fermi Paradox in a nutshell, a cosmic riddle that's as haunting as it is perplexing. But here's where things get interesting. Instead of shrugging off the mystery, scientists and thinkers have turned to imagination to fill the gaps. Some propose that advanced civilizations build Dyson spheres, colossal structures enveloping stars to harness their energy, leaving telltale infrared signatures. Others suggest the zoo hypothesis, the idea that aliens might be watching us from afar, deliberately staying hidden like observers in a galactic wildlife preserve. There's even the dark forest theory, painting the universe as a place where civilizations stay silent to avoid attracting dangerous attention. These aren't just sci-fi plots, they're serious frameworks guiding real research, like the search for extraterrestrial intelligence, or SETI, which scans the skies for unnatural radio signals or laser pulses. Yet for all the creativity, there's a counterbalance: the cold, hard math of the Drake equation. Dreamed up by astronomer Frank Drake in the 1960s, it breaks down the variables needed for intelligent life to arise: the rate of star formation, the fraction with planets, the odds of those planets being habitable, and so on. Plug in the numbers and the results swing wildly. Optimists get a universe teeming with life. Pessimists get a lonely Earth. The problem, we still don't know most of those variables. Is life a cosmic fluke, or are we just bad at looking? That tension between speculation and evidence is where the real magic happens. Take Tabby's star, for example. When astronomers noticed its light dimming erratically, some wondered if it was surrounded by an alien megastructure. The truth turned out to be dust clouds, but the very act of asking the question pushed us to study stellar behavior in new ways. Or consider the WOW signal, a brief radio burst in 1977 that still hasn't been explained. Was it a cosmic hiccup or a fleeting hello from across the void? We may never know, but the mystery keeps us searching. So here's the real question Fermi's paradox leaves us with. Are we truly alone, or is the universe playing the ultimate game of hide and seek? The answer might not lie in choosing between science and imagination, but in letting them work together. After all, every telescope pointed at the stars, every algorithm sifting through radio noise began as someone's wild idea. And as we build better tools like next-generation observatories and AI-driven data analysis, we're not just hunting for aliens, we're testing the boundaries of what's possible, one imaginative leap at a time. Point Hubble toward what looks like an empty patch of sky, let it stare for days, and something miraculous happens. That blank canvas fills with galaxies. Not dozens, not hundreds, but thousands, each a swirling island of stars so distant their light left them when Earth was young. The Hubble Deep Field image did more than expand our cosmic map. It gave us a time machine. Those specks of light aren't just far away, they're snapshots of the universe as it existed billions of years ago, a photo album of cosmic infancy. It's like uncovering buried chapters of a history book we didn't know existed, pages glowing with the birth of stars long since faded. Then came James Webb, Hubble's successor, with its infrared eyes peeled for the universe's earliest whispers. What it found stunned everyone: galaxies too massive, too mature, existing far earlier than our models predicted. These cosmic toddlers, thriving when the universe was barely 2% of its current age, shouldn't have had time to grow so sophisticated. Yet there they were, defying textbooks like uninvited guests at a party. Neil deGrasse Tyson's words ring louder than ever. The universe is under no obligation to make sense to you, and that's the thrill. Every time we build a better window to the cosmos, it hands us new puzzles wrapped in old light. But here's the beautiful twist. These discoveries don't just baffle scientists, they ignite storytellers. When astronomers revealed galaxies colliding in a gravitational dance, fantasy authors spun tales of civilizations clinging to rogue planets, surfing the tidal forces. The pillars of creation, those towering stellar nurseries, became backdrops for epic space operas. Even the impossible Galaxies Web found have writers reimagining cosmic timelines. What if life had a head start elsewhere? What if we're the latecomers to a universe already teeming with ancient cultures? Science and fiction feed each other in this endless loop. A telescope's data becomes a novelist's setting. A writer's what-if nudges a physicist to run the numbers. Consider dark matter. Invisible, mysterious, it's the perfect plot device for tales of hidden worlds. Yet it's also the reason real galaxies don't fly apart. A mystery scientists are racing to solve with detectors buried deep underground. The line between tool and inspiration blurs until you can't tell where the equations end and the daydreams begin. So the next time you see a headline about a telescope spotting some distant wonder, remember, you're not just looking at data. You're witnessing the first draft of tomorrow's myths, the raw material for both scientific revolutions and bedtime stories. The universe writes the plot twists, we're just learning how to read them. 1995 changed everything. For centuries, we'd wondered if other stars had planets, but proof was as elusive as a whisper in a storm, until astronomers Mitchell Mayer and Didier Queloz spotted 51 Pegasi b. This Jupiter-sized world, orbiting its star in just 4 days, wasn't just the first confirmed exoplanet. It was a key turning the lock on the cosmic zoo. Suddenly, the universe felt less like a solitary stage and more like a crowded neighborhood. Early science fiction had painted alien worlds as either mirror images of Earth or surreal dreamscapes. Think of H.G. Wells' blood-red Martian canals or Star Trek's M-class planets, all conveniently human-friendly. Reality turned out stranger. Take hot Jupiters like 51 Pegasi b, gas giants roasting close to their stars, or diamond planets where crushing pressure might crystallize carbon into gems. These aren't the settings of pulp novels, they're catalog entries in NASA Exoplanet Archive. Yet the most tantalizing discoveries orbit in the Goldilocks Zone, not too hot, not too cold, where liquid water could pool. TRAPPIST-1 rocky worlds, 3 of them in that sweet spot, sparked a frenzy. Could one of them hold an ocean, an atmosphere, or even, dare we say it, life? That's where art collides with data. Scientists can measure a planet's mass, orbit, even the molecules in its air, but turning numbers into landscapes takes imagination. Enter artists like NAS, a conceptual design team who blend spectroscopy with creativity. When the James Webb Telescope detected carbon dioxide on exoplanet WASP 39b, illustrators didn't just sketch a hazy sphere, they envisioned a world of perpetual twilight with silicate clouds raining glass. TRAPPIST-1 planets might have crimson skies from cool red sunsets, or tidal-locked hemispheres where one side forever bakes and the other freezes. These visuals aren't just pretty, they're hypotheses. A painting of a methane-rich world could inspire a scientist to tweak a climate model, asking, could life evolve here under alien rules? Which brings us back to fiction's role. When Arthur C. Clarke wrote about Europa's hidden ocean in 2010, Odyssey 2, it seemed fantastical. Now, we're designing probes to crack its icy shell. The line between sci-fi prophecy and scientific target keeps blurring. So when you hear about a super Earth with a hydrogen haze or a lava world with molten seas, ask yourself, are these tomorrow's vacation spots or just cosmic curiosities? The answer might depend on how boldly we keep dreaming and how carefully we keep looking. Vera Rubin peered through her telescope in the 1970s, tracking the motion of stars at the edges of galaxies, and found something that shouldn't be, stars whirling so fast they should have been flung into the void, yet something unseen held them in place. It was like watching the outer horses on a carousel spin just as fast as the inner ones, defying every law of motion. The only explanation, an invisible hand, a gravitational glue we couldn't see, dark matter. Medieval mapmakers scribbled "Here be dragons" at the edges of their charts, but Rubin's dragons were real, and they were rewriting cosmology. Today, we know dark matter outweighs visible matter 5 to 1, weaving an unseen scaffold that holds galaxies together. But what is it? Theories abound, each more fascinating than the last. WIMP, weakly interacting massive particles, are the leading suspects, ghostly entities that barely touch ordinary matter except through gravity. Then there are actions, hypothetical particles so lightweight they flit through space like cosmic fireflies. Some scientists even toy with the idea of primordial black holes, remnants of the Big Bang lurking in the darkness. The hunt for these phantoms is anything but passive. Deep underground, in labs shielded from cosmic noise, detectors wait for the faintest tick of a WIMP collision. At CERN, particle smashers recreate conditions from the universe's first moments, hoping to shake loose a clue. Yet here's the twist. The tools we use to chase dark matter are as imaginative as they are technical. Physicists see it by watching galaxies bend light like a funhouse mirror, a phenomenon called gravitational lensing. They simulate its grip on supercomputers, tracing how it sculpts the cosmic web. It's detective work on a galactic scale, where every null result, every experiment that doesn't find dark matter tightens the noose around the truth. And just like the cartographers of old, we're drawing maps of the unknown, labeling the gaps with equations instead of dragons. The difference: today's explorers wield math and particle accelerators, turning here be dragons into here be data. The mystery isn't just unsolved, it's alive, pulsing in every shadowy corner of the cosmos, daring us to look deeper. Imagine the universe as a grand symphony, but instead of strings on a violin, the notes are played by tiny, vibrating filaments of energy, cosmic threads so small, 1 billion of them could dance on the head of a pin. That's the heart of string theory, a radical idea that rewrites the rules of reality by suggesting everything in existence, from the stars to your fingertips, is made up of these minuscule, oscillating strings. Michio Kaku once compared it to fish in a pond, blissfully unaware of the world above the water's surface. To them, raindrops might seem like mysterious disturbances from another realm, just as we might be oblivious to the higher dimensions where these strings truly vibrate. The math behind string theory is elegant, but here's the catch. It requires at least 10 dimensions to work, far beyond the 4 we experience. Picture a spider's web glistening with dew. To an ant crawling along a single thread, the web seems one-dimensional, but from our vantage point, we see the full, intricate tapestry. String theorists argue we're like that ant, trapped in a limited view of a far richer cosmos. Yet for all its beauty, the theory faces a glaring hurdle. We can't yet test it. No microscope can peer close enough to spot these strings, and no particle collider has the energy to reveal them. That's why critics call it more philosophy than physics, a dazzling hypothesis without a clear path to proof. But what if our universe isn't the only one? Enter the multiverse, a dizzying idea where countless universes bubble up like foam in an infinite ocean, each with its own laws of physics. Some might have stars and planets like ours, others could be barren wastelands or realms where time flows backward. This isn't just sci-fi fodder, it's a serious, if controversial, extension of string theory. The catch, proving it seems impossible. If other universes are forever beyond our reach, how do we study them? Some scientists look for cosmic fingerprints, like odd patterns in the afterglow of the Big Bang that might hint at a collision with another universe. Others argue the multiverse is untestable by definition, a metaphysical escape hatch for questions we can't answer. Yet these ideas have seeped into pop culture, shaping stories like Doctor Strange, where alternate realities fold like origami. The film's kaleidoscopic visuals aren't just eye candy. They're inspired by real theories of warped space-time and hidden dimensions. Even quantum research plays with multiverse-like concepts, like the many worlds interpretation, where every decision spawns a new timeline. The line between science and speculation blurs, leaving us with a thrilling thought, perhaps the wildest ideas. The ones that feel like they're pulled from a comic book are the very ones pushing us toward tomorrow's breakthroughs. After all, wasn't the atom once just a philosopher's dream? A supercomputer sifts through millions of telescope images, hunting for cosmic mirages, galaxies warped into rings and arcs by the gravity of invisible dark matter. A task that once took astronomers months now takes minutes, thanks to machine learning algorithms trained to spot these gravitational lenses hidden in the noise. This isn't science fiction. It's happening right now at observatories worldwide, where AI has become the ultimate research assistant, crunching data at scales no human team could match. But here's the twist. These algorithms aren't just finding known phenomena, they're stumbling onto oddities that defy classification, like cosmic Rorschach tests begging for interpretation. Take NASA Kepler telescope, which collected light curves from 200,000 stars. Buried in that avalanche of data were exoplanets, thousands of them, but also bizarre flickers that didn't fit any model. Enter AI, which flagged the strangest signals for human review, leading to discoveries like Tabby's star, with its erratic dimming that briefly had scientists whispering alien megastructure, the real revelation. Machines excel at finding needles in haystacks, but it still takes a human to ask, what kind of needle is this? Meanwhile, tools like DALL-E and Mid-Journey are riffing on cosmic themes, generating nebulae that never existed, vibrant swirls of gas and dust that look ripped from Hubble's archives. At first glance, it's just eye candy, but dig deeper. When researchers feed these synthetic universes into training datasets, they're teaching AI to recognize patterns even nature hasn't produced. It's like giving a musician every possible chord combination before they compose a symphony. The implications ripple outward. Could an AI trained on every known quasar and supernova simulate a galaxy collision we've never witnessed? Might it propose a new class of black hole purely from mathematical aesthetics? Yet for all their prowess, algorithms lack the spark that ignites true breakthroughs, the why behind the what. Einstein didn't derive relativity by processing data. He daydreamed about riding light beams. Vera Rubin chased dark matter because she refused to accept impossible stellar motions. AI can connect dots, but humans insist on drawing constellations between them. Consider the Event Horizon Telescope's black hole image. Machine learning helped reconstruct the data, but it took a team of scientists to interpret the shadow's meaning, debating its implications for gravity itself. So here's the delicate balance we're striking. Let AI handle the grunt work, the petabytes of radio static, the exoplanet transits buried in noise, while humans focus on the questions machines can't frame. Together, they're rewriting the playbook for discovery. The next paradigm shift might come from a neural network spotting an anomaly in quasar light, or from a grad student inspired by an AI's hallucinated nebula, scribbling a new equation at 3 a.m. The universe doesn't care who or what unlocks its secrets. It only asks that we keep looking. Vincent van Gogh painted Starry Night from the barred window of an asylum, swirling the cosmos into something alive. The stars pulsing, the sky churning like liquid. He called it the terrible need for religion, but what he captured was the awe of the infinite, the same awe that grips astronomers peering through telescopes today. Art and science have always shared this language of wonder, each translating the cosmos through different lenses. Look at the intricate celestial maps of ancient Babylon, etched in clay, not just as navigation tools but as love letters to the heavens. Or the Golden Record, launched with Voyager in 1977, a mosaic of Earth sounds from Bach to whale songs, meant to serenade any alien listener. These aren't just artifacts, they're bridges between the measurable and the sublime. Lynette Cook's paintings take this further, blending hard science with brushstrokes. When astronomers discovered the first exoplanets, they were just lines on a graph until Cook rendered them as worlds. Her depiction of HD 209 458b, a gas giant with sapphire clouds, isn't guesswork. It's based on spectral data hinting at silicate particles scattering blue light. Her art answers a question equations can't. What would it feel like to stand there? Similarly, the Hubble Heritage Project doesn't just release raw telescope images. They're painstakingly colorized, with hues chosen to highlight chemical composition, oxygen glowing blue, hydrogen red, turning data into poetry. Astronaut Nicole Stott's words ring true. Seeing Earth from orbit rewires your brain. The thin blue line of atmosphere, the swirling marble of continents, it's a perspective that dissolves borders and sparks epiphanies. That's why NASA employs artists like Robert McCall, whose murals of space stations and Mars bases weren't just promotional. They were provocations, daring engineers to build what he envisioned. When the pale blue dot photo Earth as a speck in Voyager's grainy shot inspired Carl Sagan's iconic reflection on our fragility, it wasn't the resolution that moved millions, it was the framing. Science gave us the image, art gave it meaning. This symbiosis fuels discovery. The same awe that drives a child to paint nebulae might lead them, years later, to study astrophysics. Consider the overview effect, the cognitive shift astronauts report when viewing Earth from space, a surge of unity and responsibility, so profound it's been studied for its psychological impact. Artists try to bottle that feeling in planetarium shows and immersive installations, while scientists chase it through probes and equations. Both are reaching for the same thing, not just knowledge but connection. Whether it's a Renaissance fresco of the night sky or a modern algorithm generating 3D exoplanet landscapes, the goal is identical: to make the cosmos feel knowable, and in knowing it, to find our place within it. Gene Roddenberry's Star Trek communicator looked like pure fantasy in 1966, a handheld device letting crewmates chat across vast distances with no wires in sight. Fast forward 3 decades, and Motorola engineers openly credited that sci-fi gadget as inspiration for the first flip phones. This wasn't a one-off fluke. The show's tricorders, tablet computers, and even voice-activated AI found real-world echoes in medical scanners, iPads, and Siri. But here's the fascinating part: Star Trek didn't just predict gadgets, it shaped the ambitions of scientists. Dr. Mae Jemison, the first black woman in space, cited Nichelle Nichols' Uhura as her childhood motivation to join NASA. When she boarded the space shuttle in 1992, she carried a Trek insignia, closing the loop between fiction and reality. Arthur C. Clarke took this predictive power even further. In 1945, while radar technicians were still tinkering with bulky ground stations, he published a paper detailing geostationary satellites orbiting relays that could bounce signals globally. Critics dismissed it as fantasy. 12 years later, Sputnik beeped into history, and by 1965, Clarke's extraterrestrial relays became Early Bird, the first commercial comms satellite. His vision didn't stop there. 2001, A Space Odyssey imagined video calls, AI pilots, and space stations with eerie accuracy, proving that sci-fi's greatest value isn't just guessing the future, but giving engineers a blueprint to build it. Then there's The Martian, Andy Weir's novel-turned blockbuster about an astronaut surviving alone on Mars. What seemed like gripping fiction became required reading at NASA at Jet Propulsion Lab. Scientists praised its hyper-accurate botany and chemistry, like using hydrazine to make water, and the agency even invited Weir to consult on real Mars mission protocols. The book's pirate ninja orbital maneuver, a risky slingshot around Earth, sparked serious discussions about emergency return trajectories. Fiction had crossed into textbook. So are sci-fi writers modern-day prophets? Not exactly. They're more like cosmic playground designers, building sandcastles of what if that scientists later fortify with steel and math. When Isaac Asimov dreamed of robots governed by ethical laws, he didn't invent AI, but he framed debates we're still having about machine morality. Black Mirror episodes exploring digital consciousness don't code neural networks, but they force us to confront questions tech CEOs gloss over. The line between speculative fiction and R&D blurs because both start with the same spark: a human staring at the unknown and refusing to accept impossible. The next time you watch a spaceship warp across a screen or read about colonists on Europa, remember, those stories aren't escapism. They're rehearsal. Every flipped switch on the Starship Enterprise, every line of dialogue in Interstellar, every alien ecosystem in Avatar is a challenge thrown down to science. Catch up if you can. And history shows we usually do. Standing under a meteor shower, you feel it, that deep, wordless pull as streaks of fire slice through the night. Your breath catches, time seems to slow. This isn't just beauty, it's a neurological event. Scientists studying awe, that spine-tingling response to vastness, find it lights up the brain like a cosmic fireworks display. The default mode network, responsible for self-reflection, quiets down, stress hormones dip. The prefrontal cortex, home to logic and categorization, temporarily steps back, making room for something extraordinary: a sense of connection to something far larger than yourself. Ancient cultures understood this instinctively. The Perseid meteor showers weren't just celestial events to the Greeks, they were sacred, tied to the tears of St. Lawrence. Indigenous Australians wove meteor trails into Dreamtime stories, mapping the sky as a living tapestry. Today, we have fMRI scans to explain why these moments feel transcendent, but the effect is the same. Whether you're a Babylonian priest tracking comets or a modern astronaut gazing at Earth from orbit, wonder rewires you. Research from Stanford reveals something even more fascinating. Awe doesn't just feel good, it changes behavior. Participants who spent time staring at towering redwoods or even watching videos of the Hubble Deep Field became more generous in lab experiments, more curious, more open to collaboration. It's as if the brain, confronted with the incomprehensible, resets its priorities. Suddenly, petty grievances shrink, creativity spikes. This might explain why civilizations from the Maya to the Mesopotamians aligned temples with celestial events. Rituals under the stars weren't just about tracking time. They were collective awe therapies, bonding communities through shared wonder. But here's the twist. Our brains seem engineered for this dance between mystery and mastery. The same dopamine rush that rewards us for solving a puzzle also floods our system when we encounter the unsolved. Take neutron stars, objects so dense a teaspoon would weigh 1 billion tons. We can calculate their spin, even model their collisions, yet they still feel like magic. That tension between knowing how they work and being stunned that they exist at all is where exploration thrives. Ancient astronomers charted constellations to navigate. Modern astrophysicists simulate multiverses. The tools evolve, but the drive doesn't. We're compelled to reach beyond what we understand, not in spite of uncertainty, but because of it. So the next time you tilt your head back to watch the Milky Way, remember, you're not just stargazing. You're tapping into a primal loop of curiosity and reward, one that's propelled humanity from cave paintings to cosmic probes. The universe invites us to marvel first, question later. And in that space between awe and analysis, discovery is born. In 2007, a radio telescope in Australia picked up a blip of energy so intense it burned brighter than 500 million suns, and then, just as suddenly, it vanished. Lasting mere milliseconds, this fast radio burst, or FRB, wasn't just a cosmic oddity. It was a siren call from the depths of space, a mystery that would send astronomers scrambling for answers. Since then, we've detected hundreds of these fleeting signals, some repeating in unpredictable patterns, others flashing once and never returning. Their origins still up for grabs. One leading theory points to magnetars, neutron stars with magnetic fields so powerful they could strip the data from your credit card from halfway across the galaxy. When these hypercharged stars crack under pressure, they might release bursts of energy visible across the universe. Then there's the more speculative idea: could FRBs be alien beacons, intentional signals from civilizations far beyond our own? The truth is, we don't know yet, and that's what makes them thrilling. These bursts aren't just cosmic static, they're invitations to imagine, to push the boundaries of what we think is possible. Now, shift gears to 2017, when a cigar-shaped object tumbled through our solar system, moving too fast to be bound by the sun's gravity. Named Oumuamua Hawaiian for Scout, it was the first known visitor from interstellar space. At first, astronomers debated whether it was a comet or an asteroid, but Oumuamua refused to fit neatly into either box. It lacked a comet's telltale tail, yet it accelerated as if nudged by some unseen force. Enter Harvard astrophysicist Avi Loeb, who dropped a bombshell hypothesis. What if Oumuamua wasn't a natural object at all, but a piece of alien technology, a solar sail or derelict probe? The scientific community bristled, but Loeb's point wasn't to declare proof. It was to challenge the limits of our assumptions. After all, when faced with the unprecedented, shouldn't all possibilities be on the table? What ties these two puzzles together is the way they force science to dance with uncertainty. Fast radio bursts and Oumuamua don't just defy easy answers. They demand creativity, the kind that blends rigorous math with bold speculation. When a repeating FRB was traced to a distant dwarf galaxy, it didn't just solve a mystery, it spawned new ones about the environments that could produce such extreme energy. Similarly, Oumuamua's odd trajectory led researchers to consider exotic natural explanations, like hydrogen icebergs evaporating in sunlight, a concept no one had seriously entertained before. These aren't just academic exercises, they're reminders that the universe loves to surprise us. Every unexplained signal, every rogue interstellar guest, is a test of our willingness to say, "We don't know yet, but let's find out." And that's the real lesson here. Whether it's a millisecond burst of radio waves or a strange skyscraper-shaped rock zooming past Pluto, cosmic mysteries don't just fill textbooks, they stretch imaginations. The history of astronomy is littered with impossible phenomena that later became cornerstones of science. Pulsars were once mistaken for alien distress calls. Quasars baffled researchers for years. Today's head-scratchers might be tomorrow's Nobel Prizes, but only if we're brave enough to entertain the wildest questions. After all, the line between outlandish theory and groundbreaking discovery has always been thinner than we think. Time isn't the steady river we imagine. It's more like a stretchy fabric, warping under the weight of planets and stars. Einstein's theory of relativity revealed this shocking truth. Time slows down near massive objects or at high speeds. We're not just talking about abstract math. Your phone's GPS relies on this daily. Satellites orbiting Earth experience time slightly faster than we do on the ground. And if engineers didn't account for that difference, your navigation apps would misplace you by miles within minutes. That's relativity in action, quietly shaping reality while we scroll through maps. Now compare that to Hollywood's take. Back to the Future's DeLorean barrels through time at 88 miles per hour, fueled by a glittering flux capacitor. It's thrilling fiction, but the science, not so much. Real-time travel wouldn't need a plutonium-powered sports car. It might require a black hole's gravity or a spaceship nearing light speed. Yet here's the funny part. Einstein's equations do allow for time loops under extreme conditions, like spinning cosmic strings or wormholes. Theoretical physicist Kip Thorne even calculated that a stable wormhole could function as a time machine, though building one would demand energy densities we can't fathom. Meanwhile, quantum mechanics adds another twist. Experiments with entangled particles where changing one instantly affects its partner, no matter the distance, hint at phenomena that seem to ignore time's arrow. Some interpretations suggest particles might influence each other backward in time, a concept called retrocausality. It's not quite Marty McFly altering his parents' first meeting, but at the quantum scale, cause and effect get slippery. Researchers at the University of Vienna sent photons on convoluted paths where their future states appeared to influence past decisions, bending intuition like a pretzel. So is time travel possible? Relativity says technically yes, but good luck booking a ticket. Quantum physics whispers maybe in ways we don't yet understand, and pop culture. It keeps us dreaming, turning cosmic curiosity into stories that inspire real scientists. After all, the same year Back to the Future hit theaters, a young physicist named Ronald Mallet was scribbling equations for a time machine based on laser loops, proving that sometimes the line between movie magic and scientific pursuit is thinner than a flux capacitor's glow. Picture this: a robotic lander touches down on Mars. its metal feet crushing the rust-colored soil as it begins searching for signs of life. But what if, in that moment, we accidentally smother the very existence we're trying to discover? The microbes hitching a ride from Earth's stubborn stowaways on spacecraft could overwhelm native Martian organisms before we even detect them. This isn't just science fiction, it's a real ethical quandary known as planetary protection, and it forces us to ask, do we have the right to colonize worlds that might already harbor life, however tiny or strange? NASA's Perseverance rover was baked at 230 degrees Fahrenheit for days to sterilize it, yet some extremophile bacteria might still survive. The dilemma echoes Avatar's Pandora, where humans bulldoze an ecosystem without understanding its interconnected genius, except this time, the blue world isn't a CGI fantasy. It's Mars, Europa, or Enceladus waiting in the cosmic shadows. Indigenous cosmologies offer a different lens. The Maori see the night sky as the sacred cloak of Ranginui, the Sky Father, while Navajo traditions teach that celestial bodies are living beings deserving respect. These perspectives don't just romanticize nature, they frame the universe as a web of relationships, not a checklist of resources to exploit. When Western science debates terraforming Mars, it often centers on technical feasibility. Can we warm the planet, melt its ice, thicken its atmosphere? But indigenous wisdom presses deeper. Should we? The irony is palpable. On Earth, we're scrambling to undo environmental damage caused by unchecked expansion, yet we're poised to repeat those mistakes light years away. Sustainability isn't just a buzzword here, it's survival. The International Space Station recycles 90% of its water, a necessity in the closed loop of orbit. Future lunar bases might mine ice for oxygen and fuel, while asteroid prospectors could harvest metals without scarring terrestrial landscapes. But true cosmic stewardship goes beyond pragmatism. Imagine missions designed like forest ecosystems, zero-waste habitats that leave moons and planets healthier than we found them. After all, if we can't balance exploration with reverence, we risk becoming the invasive species of the galaxy, spreading, consuming, and moving on until there's nowhere left to go. The stars urge us to choose wisely. They're not just destinations, they're mirrors reflecting back our values. Will we be conquerors, or will we finally learn to walk lightly, carrying not just our ambition, but our humility into the cosmos? On September 14, 2015, at precisely 9:50 in the morning Universal Time, a ripple passed through Earth, a distortion so minuscule it stretched a 4-kilometer-long tunnel by less than 1,000th the width of a proton. Yet that whisper from the cosmos, detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, shattered our silent view of the universe. What LIGO captured wasn't light or radio waves, but the reverberation of spacetime itself, the death spiral of two black holes, each 30 times the mass of our Sun, colliding 1.3 billion years ago. The signal, translated into sound, was a fleeting chirp, rising in pitch before abruptly cutting off. Astrophysicist Jana Levin likened it to the universe singing, its melody written not in notes but in the warping fabric of reality. Think of it like this: if telescopes are our eyes peering across the electromagnetic spectrum, gravitational wave detectors are our ears. For centuries, astronomy was a silent film, gorgeous, but missing half the story. Now we've plugged in the speakers. Those black holes didn't just crash, they rang spacetime like a bell, sending vibrations through the cosmic medium at light speed. The event released more energy in gravitational waves than all the stars in the observable universe combined emitted as light in that same instant. Yet by the time those ripples reached us, they'd faded to near nothing, requiring instruments so precise they can measure changes smaller than an atom's nucleus. This wasn't just a technical triumph, it was a paradigm shift. Einstein predicted gravitational waves in 1916, but doubted we'd ever detect them. Even he underestimated the universe's flair for drama. The chirp LIGO heard wasn't a lone voice, it was the first note in a symphony. Since then, detectors have caught neutron stars colliding in a shower of gold and platinum, black holes merging in ways that defy expectations, even mysterious mass gap objects that don't fit known categories. Each event peels back another layer, revealing a cosmos far more dynamic and violent than we imagined. Consider how differently we perceive music versus noise. Before LIGO, the universe seemed static, its changes unfolding too slowly for human timescales. Now, we know it's a cacophony of collisions, explosions, and mergers, playing out in a medium we're only beginning to sense. The next generation of detectors, like the space-based LISA mission, will extend our hearing to lower frequencies, catching the slow-motion dances of supermassive black holes. We're not just observers anymore, we're audience members at the grandest performance of all, learning to decipher the rhythms of existence itself. Einstein called it spooky action at a distance, a phrase that sounds more like a ghost story than physics. Yet quantum entanglement, the phenomenon that unnerved him, is very real. Picture two electrons born from the same atomic event, spinning in perfect sync, no matter how far apart they drift across a lab bench or across the galaxy. Change the spin of one, and its partner instantly mirrors that change, as if flipping a coin in Tokyo makes another in Paris land heads up simultaneously. This isn't telepathy, it's the universe operating with hidden threads we're only beginning to grasp. The implications are staggering. In classical physics, nothing travels faster than light. It's the cosmic speed limit. But entangled particles seem to bypass this rule entirely, communicating instantaneously. Einstein hated this idea, insisting there must be hidden variables at work. Yet decades of experiments, like those testing Bell's theorem, have confirmed entanglement's bizarre reality. Doctor Who played with this concept in its Quantum Entanglement romance, where two characters remain psychically linked across time and space, a whimsical take on a scientific truth that's stranger than fiction. What makes entanglement so revolutionary isn't just its defiance of classical physics, it's the way it forces us to rethink reality itself. The universe might not be a collection of separate objects, but a vast web where particles remain deeply connected regardless of distance. Some theories suggest these correlations emerge from higher dimensions or a fundamental layer of existence we can't yet perceive. Others argue that spooky action reveals a flaw in how we define space and time, hinting that they're emergent properties rather than absolute frameworks. Today, entanglement isn't just a laboratory curiosity, it's the backbone of quantum computing and ultra-secure communication. Chinese satellites use entangled photons to create unhackable encryption keys, while tech giants race to build quantum networks. Yet for all its practical promise, the deeper mystery remains. Entanglement shows us that the universe is far more interconnected, far more mysterious than Einstein ever dreamed. And that's the real magic, not just the science, but the door it opens to new ways of seeing everything. What if everything around us, the stars, the trees, even the screen you're staring at, wasn't real, but lines of code in an unfathomably advanced simulation? Philosopher Nick Bostrom posed this unsettling idea in 2003, arguing that at least one of three possibilities must be true. Either intelligent civilizations never reach the technological stage to create simulations, they choose not to run them, or we're almost certainly living inside one. His reasoning hinges on simple math. If future civilizations could simulate conscious minds, they'd likely create countless virtual worlds, billions, trillions, far outnumbering the single, base reality. Statistically, the odds tilt heavily toward us being digital constructs rather than biological originals. Elon Musk famously embraced this logic, quipping that the chances we're in base reality are 1 in billions. This isn't just futurism, it's a modern twist on ancient questions. Plato's cave allegory imagined prisoners mistaking shadows for reality, while Hindu texts describe the universe as Maya, an illusion. The Matrix turbocharged the idea for pop culture, with Keanu Reeves waking up in a vat of goo, his entire life a neural hallucination fed by machines. But simulation theory differs in one crucial way. It's not about deception, but inevitability. If creating conscious simulations becomes possible, the sheer number of simulated beings would dwarf those in the original universe. We wouldn't be victims of a grand trick, we'd just be statistical noise in an ancestor simulation run by post-human historians. Critics counter with practical hurdles. Simulating every atom in a universe would require impossible computational power unless the simulation only renders what observers perceive, like a video game loading graphics as players explore. Quantum mechanics adds fuel here. Particles existing in superposition until measured sound eerily like optimizations. Why calculate a falling tree's sound in a forest with no one to hear it? Even glitches fit the narrative. Ever seen a déjà vu or a fleeting visual anomaly? Simulation believers smirk. Those could be patches or data lags. But here's the mind bender. If we're in a simulation, does that make science and imagination the same thing? When Einstein conjured relativity through thought experiments, was he reverse engineering the source code? When artists dream up alien worlds, are they glimpsing other simulation parameters? Suddenly, creativity isn't just inspiration, it's debugging. The irony is delicious. The tools we use to probe reality, math, physics, art, might all be ways of hacking the system that built us. Yet the theory's real power isn't in proving we're simulated. It's in revealing how thin the line between discovery and invention has always been. Every scientific revolution, from Copernicus displacing Earth to quantum physics erasing certainty, has reshaped reality's rules. Simulation theory just takes it further, suggesting the ultimate act of imagination might be recognizing we're someone else's thought experiment. Whether that's terrifying or exhilarating depends on your perspective. After all, if we're living in cosmic code, the programmers clearly gave us one hell of a sandbox to play in. Deep beneath the Antarctic ice, in lakes cut off from sunlight for millions of years, bacteria thrive in water colder than your freezer. At hydrothermal vents on the ocean floor, where temperatures soar past 700 degrees and toxic chemicals spew from the Earth's crust, entire ecosystems flourish without a single photon of sunlight. These are extremophiles, Earth's most tenacious life forms, and they're rewriting the rules of where life can exist. If organisms can survive in boiling acid or frozen darkness right here on our own planet, what unfathomable creatures might lurk in the ammonia seas of Titan or the subterranean oceans of Europa? Astrobiologists aren't just guessing, they're using these radical survivors as blueprints for alien hunting. Take the tardigrade, a microscopic 8-legged wonder that can survive the vacuum of space, lethal radiation, and even being dehydrated to a speck for decades before springing back to life. Or the sulfur-eating bacteria in Yellowstone's scalding hot springs, thriving in conditions that would dissolve human flesh in seconds. These organisms prove life doesn't need Earth-like comforts, it just needs a loophole in chemistry. That's why NASA studies Chile's Atacama Desert, the driest place on Earth, to simulate Mars. When researchers found microbes there eking out existence in salt rocks that hadn't seen water in 50 years, it shattered assumptions about the bare minimum life requires. Now stretch that logic across the cosmos. Saturn's moon Titan, with its rivers of liquid methane, could host cells using hydrocarbons instead of water. Venus's sulfuric acid clouds might harbor floating microbes, while Jupiter's Europa might conceal entire food webs beneath its icy shell, powered by volcanic vents. Some scientists even toy with silicon-based life, an idea straight out of classic Star Trek episodes but grounded in real chemistry. Carbon builds Earth's DNA, but silicon sits right below it on the periodic table, capable of forming similar complex chains. On a scorching exoplanet where carbon burns away, silicon might be the architect of life's scaffolding. This brings us to Arrival, the film where linguists grapple with alien beings whose language isn't linear but circular, a reflection of their non-linear perception of time. The movie's genius lies in its premise. Communication with extraterrestrials might not hinge on translating words, but on rewiring how we think. Real-life astrobiologists face this challenge daily. If we discover microbes in Mars' permafrost, will we recognize their biological signatures? If an intelligent species communicates through bioluminescent pulses or magnetic fields, how would we even begin a dialogue? The SETI Institute's Messaging Extraterrestrial Intelligence project debates whether math, the universe's supposed universal language, would make sense to a species that perceives reality through entirely different senses. The search for weird life isn't just about expanding the cosmic senses. It's a mirror held up to our own assumptions. Every time we declare something uninhabitable, Earth's extremophiles laugh from their volcanic vents and radioactive pools. They're proof that life is more creative than we are, and the universe, if it's listening, might be waiting to show us just how narrow our imagination has been. Imagine the universe in its first trillionth of a second, an unfathomable speck smaller than a proton, hotter than the core of a supernova, and suddenly it doubled in size, then doubled again, and again, faster than light itself could cross the tiny space between its edges. This wasn't just expansion, it was cosmic inflation, the universe's most extreme growth spurt, stretching space itself like taffy in a fraction of an instant. The math behind this idea is so elegant, it feels inevitable. A single quantum field, dubbed the inflaton, tipped the universe into a runaway expansion that smoothed out wrinkles, set the stage for galaxies, and left behind fingerprints we can still detect today. Those fingerprints are etched into the cosmic microwave background, the afterglow of the Big Bang. Picture this: in 1965, astronomers Arno Penzias and Robert Wilson stumbled upon a mysterious static hissing from all directions. At first, they blamed pigeon droppings on their antenna, but the noise was real, the cooled remnant of the universe's fiery birth, now just 3 degrees above absolute zero. Decades later, satellites like COBE and Planck mapped this ancient light with exquisite precision, revealing subtle temperature variations no bigger than 1 part in 100,000. These tiny fluctuations are cosmic fossils, imprints of quantum jitters stretched to astronomical scales by inflation's lightning-fast stretch. Here's where it gets wild. Inflation explains why the universe looks so eerily uniform in all directions. Regions now billions of light-years apart were once cozy neighbors, smoothed by that early hyper-expansion. It's like blowing up a balloon with microscopic wrinkles, inflated enough, and the surface becomes nearly flawless. But inflation also predicts something even stranger. The universe we see might be just one bubble in an endless froth of inflating space, with other bubbles forever out of reach, each with its own laws of physics. The beauty of inflation lies in its audacity. Theorist Alan Guth proposed it in 1980, not because telescopes demanded it, but because the math clicked into place, tying up loose ends about the universe's flatness and lack of magnetic monsters called magnetic monopoles. That's science at its boldest, an idea so compelling, it reshapes reality before the evidence fully arrives. And when that evidence did come, like the precise patterns in the cosmic microwave background, it fit inflation's predictions like a key in a lock. Yet mysteries linger. What triggered inflation's sudden stop? Why did that primordial field decay into the particles we know? Some theories suggest collisions between bubble universes might leave scars in the cosmic microwave background, ghostly circles where our bubble bumped another. Others propose inflation never truly ended, with distant regions of space still inflating eternally, birthing new universes in a process called eternal inflation. The math works, but the proof, that's still out there, waiting in the whispers of the cosmos. So next time you gaze at the night sky, remember, the vast, serene expanse above you was born from chaos, a split-second frenzy that set the stage for everything. And those quiet stars, they're just the embers of a fire that once burned hotter than imagination itself. In 1994, Mexican physicist Miguel Alcubierre did something extraordinary. He took a page from Star Trek and mathematically proved that a warp drive, while wildly impractical, might not violate Einstein's laws after all. Here's how it works. Instead of trying to push a ship through space faster than light, a cosmic speed limit that can't be broken, Alcubierre imagined bending space itself. Picture a surfer riding a wave, carried forward not by their own power but by the water's motion. His theoretical drive would compress space-time in front of a ship while expanding it behind, creating a bubble where the vessel sits undisturbed. Inside this warp bubble, you wouldn't feel acceleration and relativity's rules stay intact. The catch, to rip space-time like this, you'd need negative energy, a hypothetical form of matter with anti-gravity properties. We've never observed it, though quantum mechanics teases its possibility with quirks like the Casimir effect, where empty space exerts weird pressures between metal plates. Now compare that to Interstellar's gorgeously rendered wormhole, a shimmering sphere hovering near Saturn, its interior a kaleidoscopic tunnel bending light like a funhouse mirror. Kip Thorne, the physicist who consulted on the film, insisted the visuals stay scientifically plausible. The result, a wormhole that didn't just look cool but obeyed Einstein's equations, with gravitational lensing distorting starlight around its edges. Wormholes, unlike warp drives, are direct predictions of general relativity bridges connecting distant points in spacetime, but there's a reason we've never found one. Keeping a wormhole stable would require exotic matter threading its throat to prevent collapse, and the energy demands might dwarf a star's lifetime output. Still, the math allows it, and that's enough to keep theorists and sci-fi writers dreaming. While warp bubbles and wormholes remain speculative, Breakthrough Starshot takes a radically different approach. Think small and think fast. This ambitious project envisions sending gram-sized nanocraft to Alpha Centauri, propelled not by rockets but by Earth-based lasers. A 1,000-gigawatt array would fire at light sails attached to these tiny probes, accelerating them to 20% the speed of light in minutes. At that pace, they'd reach our nearest stellar neighbor in just over 20 years. It's a clever workaround to the fuel problem. No heavy engines, just photons pushing featherweight sails. But the challenges are staggering. A grain of dust at relativistic speeds could vaporize a probe, and communicating across 4 light-years would require lasers more precise than any we've built. So, will humans ever reach the stars, or are we Earth-bound? The answer might lie in blending these ideas. Warp drives and wormholes stretch the limits of known physics, but they remind us that the universe's rulebook still has blank pages. Meanwhile, projects like Starshot prove that ingenuity can turn far-fetched dreams into engineering problems, and those history shows are solvable. Whether it's bending space-time or riding light beams, our path to the stars won't be a single breakthrough but a mosaic of crazy ideas, patient science, and maybe, just maybe, a little borrowed magic from the stories that first made us look up and wonder. Consider the force of gravity, just strong enough to hold planets in orbit, yet weak enough that you can lift your hand against it without a second thought. Now imagine tweaking that number ever so slightly, a fraction stronger, and stars would burn out in a cosmic blink, a hair weaker, and matter might never have clumped into galaxies at all. This eerie precision isn't limited to gravity. The cosmological constant, which dictates the universe's expansion rate, is balanced on a razor's edge any larger, and space would have torn itself apart before atoms could form. These delicate ratios are what physicists call fine-tuning, and they've sparked one of science's most provocative debates. Is the universe tailor-made for life, or are we just lucky? Stephen Hawking once countered the design argument with characteristic bluntness. The universe doesn't allow perfection. To him, the apparent fine-tuning wasn't evidence of a cosmic architect but a selection bias. We can only observe a universe that permits our existence, no matter how improbable its parameters. It's like a puddle marveling at how perfectly its hole fits its shape, never considering that the hole might have molded itself to the water. This self-correcting perspective is the heart of the anthropic principle, the idea that the universe's laws appear fine-tuned because, well, we're here to notice them. But what if our universe isn't the only one? Enter the multiverse, a sprawling landscape of parallel realities where every possible combination of physical constants plays out. In this scenario, most universes would be stillborn, too chaotic or sterile to host life. We just happen to inhabit the rare outlier where the numbers lined up right. It's not design, it's a statistical fluke on an unimaginable scale. String theory lends weight to this idea, suggesting higher dimensions could spawn endless bubble universes, each with its own unique physics. Some might have gravity 1 billion times stronger, others with no electromagnetism at all. We're not special, we're just the winners of a cosmic lottery we didn't know we entered. Yet the multiverse isn't without its critics. Nobel laureate Paul Davies argues that invoking infinite universes to explain fine-tuning is like using a theory of anything to explain nothing. If every possible outcome exists somewhere, science loses its predictive power. Others propose more exotic solutions, like the universe self-adjusting its constants through feedback loops, or the controversial simulation hypothesis, where our fine-tuned reality is someone else's deliberate programming. The debate reveals a deeper tension in how we seek meaning. For some, fine-tuning hints at a grand purpose. For others, it's a call to embrace our fragility in a vast, indifferent cosmos. But perhaps the most humbling thought is this: whether by design, accident, or multiversal dice roll, we're here stardust that somehow learned to measure the very forces that made its existence possible. And that, in itself, is a wonder worth pondering under the stars. Imagine crushing Mount Everest into a single sugar cube. That's the mind-bending density of a neutron star. Born from the violent death throes of a massive star in a supernova explosion, these cosmic remnants pack the mass of our sun into a sphere no wider than Manhattan. The gravity here is so intense that protons and electrons fuse into neutrons, creating a material so dense, a single teaspoon would weigh 1 billion tons on Earth. If you dropped a pebble onto its surface from just 1 meter high, it would hit the ground at half the speed of light, releasing the energy of a nuclear bomb. But neutron stars aren't just cosmic curiosities, they're alchemists. When two of these ultra-dense objects spiral into each other, their collision unleashes a fireworks show of creation. The titanic forces at play forge heavy elements like gold, platinum, and uranium, flinging them into space in glowing clouds of debris, that wedding ring on your finger. The gold in its band was likely born in a neutron star collision billions of years ago, a sparkling remnant of celestial violence. Some neutron stars spin at dizzying speeds, whirling hundreds of times per second while blasting out beams of radiation like interstellar lighthouses. These pulsars, as they're called, sweep their beams across the cosmos with such precise regularity that their pulses can be used as cosmic clocks. Some are even more accurate than atomic timekeepers on Earth. Ancient Polynesian navigators once steered by the stars, but future spacefarers might chart their course by these pulsar beacons, their rhythmic flashes cutting through the void like metronomes of the universe. Yet for all their precision, pulsars also fuel myths. When the first pulsar signal was detected in 1967, its perfect regularity had astronomers briefly dubbing it LGM-1, short for Little Green Men. They joked about interstellar messages, but the truth was just as wondrous. A spinning stellar corpse, its magnetic fields funneling energy into focused beams, lighting up the darkness like a cosmic disco ball. Whether forging precious metals or marking time across the galaxy, neutron stars remind us that even in death, stars continue to shape the universe in ways that defy imagination. In 1998, two teams of astronomers made a discovery that turned cosmology upside down. They were studying distant supernova exploding stars so bright they can outshine entire galaxies, hoping to measure how fast the universe's expansion was slowing down. The shock came when their data revealed the opposite. The cosmos wasn't breaking at all. It was accelerating, as if some invisible foot had slammed on the cosmic gas pedal. The implications were staggering. Either gravity didn't work the way we thought, or something strange was pushing everything apart. That something earned a name straight out of a sci-fi novel, dark energy. The irony is thick enough to cut with a knife. Decades earlier, Albert Einstein had scribbled a term into his equations called the cosmological constant, a fudge factor to keep the universe static, as everyone then assumed it was. When Edwin Hubble later proved the cosmos was expanding, Einstein famously called the constant his greatest blunder. Yet here we are, a century later, realizing he might have been right for the wrong reason. That discarded term now looks eerily similar to the repulsive force we call dark energy, a kind of anti-gravity woven into the fabric of space itself. But what is it? One leading theory suggests dark energy is the energy of empty space, a property of the quantum vacuum where particles flicker in and out of existence. If this vacuum energy has a repulsive effect, it could explain the accelerating expansion. The trouble is, when physicists calculate how strong this effect should be based on quantum theory, their numbers overshoot observations by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros, the worst mismatch in science. This glaring discrepancy has led to wilder ideas. Maybe dark energy isn't constant at all, but a dynamic field that changes over time like an invisible fifth force. Some theories propose it's tied to hypothetical particles called quintessence, while others suggest gravity itself behaves differently across cosmic distances. Then there's the radical notion that our universe is a bubble colliding with others in a higher dimensional foam, creating the illusion of acceleration. The mystery deepens when you consider the timing. Dark energies push only overpowered gravity's pull about 5 billion years ago, coincidentally, right around the time Earth was forming. Before that, matter's gravity dominated. Now, dark energy reigns. Is this just a fluke of cosmic scheduling or a clue hidden in plain sight? For now, telescopes like Euclid and the upcoming Nancy Grace Roman Space Telescope are hunting for answers, mapping galaxies across billions of light years to trace dark energy's fingerprints. Whether it's Einstein's resurrected constant, a quantum ghost, or something beyond current physics, one thing's certain: the universe is still full of surprises, and the greatest one might be the force we can't see, hurtling us toward an unknown future. Earth sits in a cosmic sweet spot, not too close to the sun to boil away its oceans, not too far to freeze them solid. Astronomers call this the Goldilocks Zone, where conditions are just right for liquid water, that magical ingredient for life as we know it. But our planet's perfection isn't just about distance. It's a symphony of finely tuned variables, a stable orbit, a protective magnetic field, an atmosphere thick enough to insulate but thin enough to let sunlight through, and even a massive moon that steadies our axial tilt, preventing wild climate swings. Tweak any one of these and Earth could have been as barren as Venus or as desolate as Mars. Consider Kepler 442b, an exoplanet 1,200 light-years away that orbits its own Goldilocks zone. Roughly twice Earth's mass, it basks in the gentle glow of an orange dwarf star, receiving just enough light to potentially host liquid water. On paper, it's a promising candidate, but that's where the similarities end. Unlike our sun, orange dwarfs are prone to violent flares that could strip atmospheres. Kepler 442b might also be tidally locked, with one side forever scorched and the other frozen. Even in the habitable zone, the devil's in the details, which raises the tantalizing question: is Earth a cosmic fluke, or just one of countless lucky winners in a universe teeming with life-friendly worlds? The numbers suggest optimism, with billions of galaxies, each hosting billions of stars, and many of those stars circled by planets. The sheer scale seems to guarantee repetition. Statistically, there should be countless Earth twins out there. Yet the Fermi Paradox looms. If life is common, where is everybody? Astrobiologists call this the rare Earth hypothesis, the idea that while simple microbial life might be widespread, the complex chain of events that led to our biosphere, plate tectonics recycling nutrients, Jupiter deflecting asteroids, even the timing of Earth's formation, could be vanishingly unique. Imagine rolling a die 1 billion times and only once getting a sequence where every single number aligns perfectly. That might be Earth's story, but hope isn't lost for alien Earths. New research suggests life might thrive in ways we haven't imagined. Subsurface oceans on icy moons like Europa or Enceladus could harbor extremophiles in pitch-black depths. Planets orbiting red dwarfs, once written off due to tidal locking and flares, might develop atmospheres thick enough to redistribute heat. Even Venus, with its hellish surface, has a temperate layer in its clouds where microbes could theoretically float. The search for Earth's cosmic cousins isn't just about finding another blue marble, it's about testing the boundaries of life itself. Every new exoplanet discovered, from the rocky TRAPPIST-1 worlds to the Hycean planets shrouded in steam-rich atmospheres, adds another piece to the puzzle. Whether we're alone or part of a grand cosmic tapestry, the answer will rewrite our place in the universe, and that's the real magic of the Goldilocks Zone. It's not just a region of space. It's a question written in starlight, waiting for us to reply. Our brains evolved to navigate a world of 3 dimensions: height, width, and depth, yet the universe might be woven from 11. String theory's extra dimensions, curled up smaller than an atom, defy everything our senses can grasp. It's like trying to explain color to someone who's only ever seen in black and white. Edwin Abbott's Flatland, written in 1884, captured this dilemma perfectly. In his satirical novella, a two-dimensional square encounters a three-dimensional sphere descending into his plane. To the square, the sphere appears first as a dot, then a growing circle, then a shrinking one before vanishing utterly incomprehensible within Flatland's limited geometry. The sphere might as well be magic. Now imagine that same square trying to fathom not just a third dimension, but 8 more beyond that. That's us, squinting at the cosmos, trying to decode realities our neurology wasn't built to process. But here's the twist: we're not entirely helpless. Mathematics becomes our sixth sense, translating higher dimensions into equations we can manipulate. When Einstein needed to describe curved spacetime, he didn't rely on mental pictures, he leaned on tensor calculus, a language flexible enough to bend with the universe's contours. String theorists do the same, using Calabi-Yau manifolds to model those tiny, coiled dimensions. These shapes aren't just abstract scribbles, they're the hidden scaffolding of reality, as real as the chair you're sitting on, even if no microscope will ever show them to us. Art bridges the gap between abstraction and intuition. Take M.C. Escher's Relativity, where staircases twist in impossible directions, or Christopher Nolan's Interstellar, visualizing a 5-dimensional tesseract as a cascading library of time. These aren't perfect analogs, but they jolt our brains out of their dimensional comfort zones. Even virtual reality is joining the fray. Researchers at Brown University built simulations letting users touch higher dimensional objects by mapping them to vibrations and visual cues. It's not true perception, but it's closer than evolution ever intended. The irony is delicious. Our 3-pound brains, forged by natural selection to avoid predators and find fruit, are now reverse engineering the cosmos with tools our ancestors couldn't have dreamed of. We'll never see an 11-dimensional universe the way we see a sunset, but through the alchemy of math and metaphor, we're learning to dance with it anyway. And that's the real miracle, not that the universe is stranger than we imagined, but that we've found ways to imagine it at all. In a quiet corner of the internet, a retired schoolteacher clicks through images of distant galaxies, her cursor hovering over swirling spirals and fuzzy ellipticals. She's one of hundreds of thousands of volunteers on Galaxy Zoo, a project that turned one of astronomy's most tedious tasks, classifying galaxies, into a global game. What started as a way to handle the overwhelming data from robotic telescopes has become something far more profound. Proof that the universe's greatest discoveries don't always happen in labs or observatories, but on kitchen tables and college dorms, where curious minds connect the dots professionals might miss. Take the case of 15-year-old Wolf Cuckier, who landed a summer internship at NASA in 2019. Bored during his first week, he started sifting through data from the Test Space Telescope, looking for dips in starlight that might signal unseen planets. Most interns would have stuck to the script, but Wolf noticed something odd, a subtle, irregular pattern others had overlooked. That anomaly turned out to be TOI 1338b, a planet orbiting 2 stars 1,300 light-years away. A high schooler, armed with nothing but curiosity and a laptop, had found a world straight out of Star Wars. What makes projects like Galaxy Zoo and TESS so revolutionary isn't just their scale, it's their philosophy. By inviting the public to join the hunt, they tap into something primal, the human urge to explore, to label, to make sense of the unknown. When volunteers spotted the mysterious Hannes Voorwerp, a glowing green blob of gas lit by a long-dead quasar, or when amateurs flagged bizarre, yellow balls in infrared data that later revealed stellar nurseries, they weren't just assisting scientists. They were rewriting the playbook for how science gets done. This isn't just about outsourcing grunt work. It's about recognizing that imagination thrives in unexpected places. A graphic designer might notice an odd symmetry in a galaxy image that a physicist would dismiss as noise. A mechanic could spot a rhythmic pulse in radio signals that algorithms filter out. The best citizen science projects harness these diverse perspectives, creating a kind of collective intelligence no supercomputer can match, and the ripple effects go beyond data. Every time someone identifies a crater on Mars or tags a supernova in a distant galaxy, they're not just contributing to science, they're forging a personal connection to the cosmos. That retired teacher classifying galaxies, she's not just clicking buttons, she's mapping the universe's architecture. The teenager spotting an exoplanet isn't just filling time, he's stepping into the shoes of Galileo, Kepler, and Sagan. In a world where science often feels locked behind ivory towers and paywalls, these projects throw the doors wide open. They remind us that the night sky doesn't belong to telescopes or PhDs, it belongs to anyone willing to look up and wonder. And sometimes, just sometimes, the person who changes our understanding of the universe isn't wearing a lab coat. They're sitting in their pajamas, sipping coffee, and proving that discovery is a team sport. Point Hubble toward a seemingly empty patch of sky. Let its light-gathering eye stare for days, and suddenly ghosts appear. Not the spirits of folklore, but galaxies so ancient their light has traveled for over 13 billion years to reach us. This is cosmic archaeology in action, where telescopes don't just show us space, they open windows to the past. Every photon captured from these distant islands of stars is a messenger from an era when the universe was in its infancy, a cosmic fossil preserved in the amber of expanding space. Take the cosmic microwave background, that faint afterglow of the Big Bang. It's not just static on an old TV. It's the oldest baby picture of the universe, snapped when it was a mere 380,000 years old. The subtle temperature variations in this relic radiation, warmer here, cooler there, aren't random noise. They're the primordial seeds of structure, the gravitational blueprints for everything that followed. Galaxies, clusters, the vast cosmic web we see today. It's as if we've uncovered the universe's first scribbles, the handwriting of creation itself. But light isn't the only clue buried in the cosmic strata. The first minutes after the Big Bang forged the universe's simplest elements, hydrogen, helium, and trace amounts of lithium, in a process called Big Bang nucleosynthesis. The ratios of these elements, measured in the atmospheres of ancient stars and distant gas clouds, match theoretical predictions with uncanny precision. It's like finding pottery shards at an archaeological dig, their composition revealing the conditions of an ancient kiln. These primordial abundances are the chemist's equivalent of dinosaur bones, tangible remnants of a time before stars existed to forge heavier elements. The parallels between cosmic and earthbound archaeology run deep. Just as historians piece together civilizations from pottery fragments and faded manuscripts, astronomers reconstruct cosmic history by decoding light spectra and elemental fingerprints. When researchers analyze the metal-poor stars in the Milky Way's halo, stars nearly as old as the universe itself, they're doing something strikingly similar to carbon dating prehistoric artifacts. Both fields rely on fragile evidence patiently sifted from noise to tell stories of origins, but there's a crucial difference. While human history is written in languages we must decipher, the universe's autobiography is composed in a universal tongue, physics. The same equations that describe how a stone falls on Earth also govern the collapse of a protogalactic cloud. This shared language lets us cross-check our cosmic timeline in multiple ways. The age of globular clusters, measured by stellar evolution models, aligns with the expansion rate calculated from distant supernova, which in turn agrees with the cosmic microwave background's snapshot of infancy. It's as if we've found the same historical event recorded in three independent ancient texts, each confirming the other's accounts, yet mysteries linger like missing pages in a manuscript. The first billion years of the universe, aptly named the Cosmic Dark Ages, remain shrouded because the fog of neutral hydrogen blocked light from escaping. It's like trying to study the dawn of civilization with only a handful of cave paintings to guide us. But new tools are changing that. The James Webb Space Telescope, with its infrared vision, peers through that primordial haze, catching the faint glow of the first galaxies as they flickered to life. Each new observation is a Rosetta Stone, helping us translate the universe's earliest chapters. What makes this archaeological dig so exhilarating is its scale. Unlike Earth's layered ruins, the cosmos preserves its entire history simultaneously. When you look at the Andromeda Galaxy, you're seeing light from 2.5 million years ago, a snapshot from when early humans were just mastering fire. Gaze at a quasar 10 billion light-years away, and you're witnessing the universe's riotous adolescence, a time of galactic collisions and voracious black holes. The night sky isn't just a spacescape, it's a timescape offering a living museum where every exhibit hangs in its proper epoch. So the next time you see an astronomy headline about some distant galaxy, remember, you're not just reading news. You're getting a dispatch from the past, a postcard sent across eons by a universe that's always whispering its history to anyone willing to listen. And with every technological leap, from larger telescopes to more sensitive spectrographs, we're not just advancing science, we're learning to hear that whisper more clearly. Richard Feynman once said, "I can live with doubt and uncertainty. It's much more interesting." Those words capture something profound about our relationship with the cosmos. In an age where we're conditioned to demand instant answers, where algorithms serve us neatly packaged explanations at the tap of a screen, there's something radical about embracing the unknown, not as a failure of science, but as its lifeblood. The greatest discoveries in history didn't come from people who had all the answers, but from those who were unafraid to sit with the questions. Take dark matter, that invisible scaffolding holding galaxies together. We've mapped its gravitational fingerprints across the universe, yet after decades of searching, we still don't know what it is. Some might see that as a shortcoming, a hole in our knowledge. But flip the perspective, this mystery is a gift. It's a cosmic breadcrumb trail leading us toward deeper truths about the fabric of reality. Every failed detector, every unexpected result, isn't a dead end. It's a signpost pointing beyond the limits of our current imagination. The same applies to those fleeting cosmic anomalies, fast radio bursts, Oumuamua, the bizarre galaxies Webb keeps finding. It's tempting to force them into existing frameworks, to file them away as solved puzzles. But what if we let them linger as questions? When Jocelyn Bell Burnell first detected pulsars in 1967, their perfectly timed pulses seemed so artificial. She and her team jokingly labeled them LGM for Little Green Men. The truth, spinning neutron stars, was no less extraordinary. By sitting with the mystery rather than rushing to explain it away, they opened a door to an entirely new class of celestial objects. This isn't about glorifying ignorance. It's about recognizing that wonder and curiosity are the twin engines of progress. When Kepler imagined planets singing harmonies, or Einstein rode a light beam in his mind's eye, they weren't just solving equations, they were dancing with the unknown, letting it guide them to places logic alone couldn't reach. Today's researchers do the same, whether they're simulating multiverses or hunting for quantum gravity. The best science isn't a march toward absolute truth, it's a conversation with the universe, one where we're constantly surprised by the replies. So the next time you hear about an unsolved cosmic riddle, resist the urge to dismiss it as a gap in knowledge. See it for what it truly is, an invitation. The universe isn't a textbook waiting to be memorized. It's a story still being written, and every mystery is a cliffhanger designed to keep us turning the pages. After all, if we knew all the answers, what would be left to discover? Science and imagination have never truly been at odds. They're dance partners, moving in sync across the cosmic stage. Consider the wild ideas that once lived only in daydreams. Black holes, once dismissed as mathematical oddities, now photographed in stunning detail. Multiverses, once the stuff of philosophy, now debated in physics conferences. Alien civilizations, once pure fiction, now the focus of multi-million-dollar telescopes scanning exoplanet atmospheres for biosignatures. Each of these breakthroughs began with a bold what if, a moment when someone dared to dream beyond the data and then used science to chase that vision down. Think about how this plays out in the real world. When Vera Rubin stared at her galaxy rotation curves, she didn't just see anomalies, she saw the ghostly fingerprints of dark matter, an invisible force waiting to be named. When Miguel Alcubierre doodled warp drive equations, he wasn't just indulging in sci-fi fantasy. He was stress-testing Einstein's relativity, probing the boundaries of the possible. Even the search for extraterrestrial intelligence, once mocked as fringe, now commands respect with projects like Breakthrough Listen scanning millions of stars for patterns that might whisper, "We're here." This synergy isn't just about big discoveries, it's about how we approach the unknown. Science provides the rigor, the tools, the peer-reviewed scaffolding. Imagination supplies the audacity, the leaps, the stories that make data come alive. Together, they transform cold equations into narratives that resonate. The pillars of creation aren't just gas clouds, they're stellar nurseries sculpted by stellar winds. The Big Bang isn't just a model, it's the opening scene of our cosmic origin story. Edgar Allan Poe, that master of mystery, once mused, "All that we see or seem is but a dream within a dream." In a way, he captured the essence of our quest. The universe reveals itself to those who dare to question, to wonder, to blend logic with leaps of faith. So keep looking up, not just with telescopes, but with minds wide open. Share your wildest cosmic questions below, because the next great discovery might start with a dreamer's hunch, waiting for science to